Before getting into standard form, we would need to understand some concepts. Let's look at this calculation, 10 to the power of 3. What would this be equal to? 10 to the power of 3 equals to 1000. How about 10 to the power of 4? 10 to the power of 4 equals to 10,000. Pause and have a quick go at figuring out what the answer to these calculations would be. You can probably see a pattern. As we move upwards in the power, the number is increasing by a factor of 10. And as you move downwards through the powers, the number is decreasing by a factor of 10. You may have realized another pattern, a special feature of 10 when it has a power. The power on top of the 10 indicates the number of zeros that appear after the 1 if the power is positive. 10 to the power of 3 has 3 zeros after the 1, which is 1000. And 10 to the power of 9, for example, has 9 zeros after the 1, which equals to 1 billion. With that knowledge, what would 10 to the power of 1 equal to? Or even 10 to the power of 0? 10 to the power of 1 equals to 10, and 10 to the power of 0 equals to 1. Some might have said that 10 to the power of 0 equals to 0, but let's look at the patterns. The power on top of the 10 tells us how many zeros there are after the 1. There are no zeros after the 1, so the answer is 1. Also, since we know the number is 10 times smaller as we go down each power, 10 divided by 10 also equals to 1. Pause and have a go at writing the power of 10 that represents these numbers. How about 10 to the power of negative 1? Is it 1 followed by negative zeros? That wouldn't quite make sense. We know the answer would be 10 times smaller, so 10 to the power of negative 1 is 1 divided by 10, which equals to 0.1. How about 10 to the power of negative 2? The answer would be 10 times smaller again. 10 to the power of negative 2 is equal to 0.01. How about 10 to the negative 3? We know we could keep dividing by 10 until we reach where we need to. But there's other ways of visualizing this. When we have a negative power above 10, this tells us the number of zeros before the 1. So 10 to the negative 3 is 0.001, 3 zeros before the 1. Have a go at finding the decimal values of these numbers. There's another way to represent these decimals. We could use fractions. 10 to the power of negative 1 is 0.1, and as a fraction is 1/10, or 1 over 10. And 10 to the power of negative 2 is equal to 0.01, which is 1/100th, or 1 over 100. As the numbers get smaller, the denominator gets bigger. So 10 to the power of negative 5 is 0.00001, or 1 over 100,000. Once again, you may have seen another pattern. 100 can be represented as 10 to the power of 2. So 10 to the power of negative 2, which is 1 over 100, can be represented as 1 over 10 to the power of 2. The same can be said about 10 to the power of negative 5, which is equal to 1 over 100,000, which can therefore be represented as 1 over 10 to the power of 5. The reason it's important to represent these numbers like this is so we can recognize when we have to divide or multiply a number by 10 to the power of an integer. For example, 5 times by 10 to the power of 2 is equal to 5 times by 100, which equals to 500. How about 5 times by 10 to the negative 2? We know 10 to the power of negative 2 is equal to 1 over 10 to the power of 2. So 5 times by 1 over 10 to the power of 2 is equal to 5 over 10 to the power of 2, or 5 divided by 10 to the power of 2. Since it is a fraction, we know it represents a division. 5 divided by 10 to the power of 2 is equal to 5 divided by 100, which therefore equals to 0.05. Therefore, 10 to the power of a negative number is equivalent to a division. If a number is multiplied by 10 to the power of negative 2, this is also equal to that same number divided by 10 to the power of 2. Pause and find the equivalent calculations of these questions. To summarize, when multiplying or dividing 10 to the power of a positive or negative integer, This can be represented as either a division or multiplication.